We'll look now at how the machine actually forms an image. This diagram shows a linear probe sitting on the skin surface. I've drawn the beam in a very simplified fashion. The ultrasound beam, in fact, varies in width as it travels deeper into the tissues. So it will narrow down to a focal point and then spread out again. But for simplicity, I've just drawn it here as having a constant width. The main point I want to make here is that any object that falls within the ultrasound beam will produce echoes, and those echoes can be displayed. The machine can calculate the depth that the echoes are coming from with reasonably good accuracy using the method I've described before. It looks at the arrival time of the echo and calculates the depth from that. So the depth dimension is not a big problem. The problem is the lateral dimension in the image. The machine has no way to tell whereabouts in the beam these two objects are located. So it arbitrarily draws the echoes in the image as if they were on a single line, which represents the center line of that beam. So since the machine can't determine whereabouts laterally in the beam each object is, all objects are displayed as if they're on the center line of the beam. So this means that objects can be displaced laterally in the image by quite a significant amount. Obviously, this problem will be worse if the beam is very wide. So one of the major factors in designing ultrasound machines is to focus the beam as narrowly as possible. Unfortunately, there are physical limitations on that, and in particular the frequency is an important determinant. The higher the frequency, the better the beam can be focused, and therefore the less this particular effect becomes. Here are the three standard probe types for external use. We have a linear probe on the left, then a curved probe in the center, and a phased array or sector probe on the right. I'll discuss how each of these scans the beam in order to build up an image in just a moment. But first, let me just talk about the typical application areas for each of these probes. Linear probes are particularly well suited for areas where the skin surface is relatively flat and where it's not possible to push the probe in very much. So they are typically used on the limbs, for example, for vascular ultrasound, for musculoskeletal ultrasound, and areas like that, where you are, as I said, placing the probe on a limb. The curved probe has an advantage in that it produces a wider field of view, so it covers a broader amount of anatomy in a single image. But because of the curved face, it needs to be pushed into the patient's tissues sufficiently to get contact over the entire surface area of the probe. And that's the entire grey area that you see in this photograph. On the right, we have a far more compact probe, which is a phased array probe, quite often called a sector probe. These are used almost exclusively in echocardiography. The reason is that they are so compact. So this probe uses a very small window to get the ultrasound into the tissues. And this, of course, is perfect when, for example, you're scanning the heart through the ribs or various other windows. So the three probes are each used in different areas. The curved probe is the workhorse in the abdomen. So that's the probe typically used for abdominal scanning, for obstetric scanning, and so on. Here we have a linear probe, and I've got a series of three diagrams showing three different beam positions. So on the left we have the beam in its first position. So the machine is pointing the beam in one particular direction. It transmits and receives echoes back from the tissues. It collects those echoes and places them in the image memory, which is where the image is being built up within the machine, and it remains stationary. So the beam remains in that position until all the echoes have been received from that particular beam position. The machine has then acquired one line of echo information to form the complete image. So then in the center we see that the beam has been stepped to a new position. It's been stepped by a small increment to the right, and that process is going to be repeated. So again, the machine will transmit, receive echoes, wait until all the echoes have come back and there are no more detectable echoes, and then it will step the beam again and repeat the transmit-receive process. So this goes on until the beams have covered the entire image area. Now, I'm only showing a small number of beams in this diagram, but in fact there would be something like 100 to 200 different beam positions. With a linear probe, you'll notice that all of these beams are perpendicular to the probe face. We'll see later it is possible for the machine to steer the beam in other directions, but this is the standard direction of the beam, at right angles 90 degrees to the face of the probe. The result is, of course, a rectangular image. A feature of this image is that you've got quite a large field of view, even at the skin surface. So you get a good wide field of view, limited only by the physical size of the probe. This animation shows how a linear probe moves the beam in order to build up the information for an entire image. So the beam is perpendicular to the face of the probe, and it is stepped from one position to another, from one end of the probe to the other, in order to build up the number of lines needed to make the entire image. This animation only shows a small number of lines, but in fact there'd be 100 or 200 different beam positions in total. Now we're looking at the image formation. So this is the echo information line by line, and here we see the final image itself being built up line by line until a complete image has been formed. That's then transferred to the display and the machine starts off building up the next image. So here I've now got a diagram showing all three of these standard probe types and their scan patterns. So repeat, on the top left we have the linear probe producing a rectangular scan format. The curved probe below that scans in the same way, so it actually operates in a way identical to the linear probe, but because of the curved shape of the probe, the beams follow a fanned motion, as I've shown here, resulting in a distinctive image shape, which has the advantage that it spreads out in width as it travels deeper into the tissues. So you have a certain surface contact area, which you can sometimes call the footprint of the probe, and then the image grows wider as it travels into the tissues. So as I said, this makes this probe very popular in the abdomen because you can get a large amount of anatomy in a single image. On the right, we have the phased array or sector probe, and you'll see here it's quite different. Every beam originates from the center of the probe face, but every beam is pointed in a slightly different direction. So typically the machine will step the beam through angle steps of about 1 degree. So the beam will point in one direction, transmit and receive, and then increment by a degree, transmit and receive again. And we'll do this maybe 90 or 100 times to produce an image that's roughly 90 degrees in angle. Now the big feature of this image is the way it spreads out in depth, of course, and the fact that there is no field of view at the skin surface. So there's zero width to the image right at the skin surface. So it's obvious that this probe can only be used to look at organs that are some distance below the skin surface. But as I said, this is ideal for things like scanning the heart using the gaps between the ribs. So these are the three standard probe types used for transcutaneous imaging. Then we have invasive probes. These probes are typically used in areas where tissues overlying the area of interest cause too much degradation of the ultrasound image, or perhaps block imaging entirely of the area of interest. And of course, the things that typically do this will be air and bone. So in the pelvis, for example, we have major problems with air and with gas and bone, and therefore it's quite common to use transvaginal probes and transrectal probes to look, for example, at the prostate. Here we have a transesophageal probe, which is used in echocardiography. So the aim is that the probe tip gets very close to the aortic outflow tract and therefore produces very nice high-quality images from close up to the target tissues. The big thing about these invasive probes is that you get the probe very close to the tissues that you're imaging, which means you can use high frequencies. So the image resolution is going to be very good, and that's because the ultrasound only has to travel a short distance through the tissues. As it happens, you also get high frame rate. For the same reason, the ultrasound's only travelling a short distance, and therefore you can repeat the transmit pulses rapidly and get a high imaging rate. The standard kind of ultrasound imaging that I've been talking about, where you have a dot in the image representing each point, is called B-mode imaging. B standing for brightness, because the brightness of each dot represents the strength of the echoes. Here we have M-mode, which is, of course, as many of you will know, is used in echocardiography. It can also be used in some other areas, but that's its primary area of application. So the idea is, having done a 2D image, you select a particular line, and I've shown it here with the broken line in my diagram on the left, and in the image on the right, you may be able to see a dotted white line. So that's the line along which echo information is going to be acquired to produce the M-mode display. So the beam will be pointed down that particular beam direction, and it will be kept stationary. It won't be scanning backwards and forwards. So you stop doing the two-dimensional scanning, and you have the beam pointing in a single direction. So this is a one-dimensional image, if you like. It's just getting echoes down a single beam line. The image is displayed in the normal way, in that depth down the screen, so going from the middle of the screen down to the bottom, is increasing depth into the tissues, but the horizontal axis is a time axis. So we will get a display of how the various tissues which happen to intersect this particular beam will be moving with time. So on the lower right, we see an example where the beam has been directed through the tips of the mitral valve leaflets, and we can see the way the mitral valve opens and closes, the complex pattern that it has as it's doing that. This M-mode, by the way, has an ECG reference, which you can see in a different colour, so that you have an accurate timing reference. M-mode is very useful in that you can see dimensions, for example, ventricular dimensions. You can see the position of valve leaflets. You can see the speed at which things open. You can see the timing at which things move, etc. So there's a lot of useful information in M-mode images. The diagram at the top here, by the way, indicates the simple sort of concept of M-mode. If there's a stationary tissue, as I've shown in the diagram on the left, then that's going to be at a constant depth. So it will just be a straight line in the M-mode image. If you have another tissue that's moving down and up, so away from the probe and then towards the probe, then the image will trace out the pattern of movement of that tissue. So that's M-mode. So in summary, I've shown the way echoes are displayed on a single line, no matter whereabouts within the beam they have actually been placed, and therefore we get some degradation of the image that's caused by this. We'll look at that in more detail later. I showed you the three standard kinds of external probes, linear, curved, and phased arrays, and I showed you the different scan formats that they have, and therefore the different image formats. And I briefly discussed typical applications. I then showed you an example of an invasive or endocavity probe and talked about the particular advantages that has. And then finally, I just talked about the term B-mode, which is standard grayscale imaging, and then explained what M-mode is.